So this problem is really sort of basic to statics. You should be able to do this in your sleep. Certainly by the end of this lab, you should be able to do it by the end of sleep, because we're going to do this problem in sort of somewhat different variations several times. So we'll go over how to solve that in a bit. I'm going to go back to me. And then I'm going to share the screen here. So what we're doing is we're going to be looking at the reaction to support stage, just sort of like I drew on the board there. What you have at your disposal at this point in statics is really sort of the three sort of, I don't know if I call them pillars, but I think of them as pillars. You have the ability to draw free body diagrams because you know the connection types, and then you have the ability to solve problems because you have the equations of equilibrium. With those three tools, you can really pretty much get through all of statics. But what I want to emphasize today is the use of the steps that Joanne has outlaid in class. I wanted to point out some of the highlights for them and some of the reasons for that. But the first reason that I think the steps are pretty good is that probably in your head you're already sort of thinking through those processes, but probably not in a formalized way and in an organized way. So doing these steps helps organize your problem solving that's in your head. And the second thing that I wanted to talk about is the fact that it really sort of gives you a way to solve any problem. I know that when I took statics, there was no sort of formalized way to attack problems, and I really could have benefited from a set of these steps. There are certainly some problems that I look at, particularly when we get into the 3D stuff with multiple unknowns, like maybe 6 or 7 unknowns with multiple bodies. It doesn't always seem so clear to me which is the right way to go. And by doing these steps, it'll really sort of help you out. Well, and lastly, it helps ensure less errors. If you follow the same procedure every time, you're less prone to errors. And that's a pretty proven fact worldwide. That's why they have checklists on airplanes, keep people from crashing, that sort of thing. So I really insist that you use this methodology. And I have this short video from the movie, The Battle of Britain. The Battle of Britain was in World War II. The Nazi Germans had invaded and taken over France, and they had already invaded Poland, and they were really sort of looking like the world dominant force that was going to capture all of Europe. And they hadn't invaded Russia yet, but they had to go take care of their enemy, England, and so they tried to take over England first by air, and it was done in the autumn of 1940. Anyways, big pivotal moment in the war. Really, it's the point where the Germans lost the war, even though the war went on for another 4 or 5 years. This battle really sort of changed the course of history. We'd probably all be speaking German if these guys hadn't won. Anyway, what I want to do is play this video, and if you can, watch it yourself. But let me play it for you so you can hear it.
Audio isn't coming through.
All right. You'll have to watch it yourselves. You could just it's only 46 seconds long. You could watch that really quickly. That'd be great.
Hey, Rob, I don't think the lab module is posted for today. It's not published.
Okay. Thought I had. Let me look. It says it's published.
Try refreshing Canvas, maybe.
Yeah, I'm showing that it's published. Oh, not there. Okay. All right. got the overall published. There's the individual published, and then there's the overall published. Anyways, have a look at that video. And for those of you that don't know, Hun is a derogatory term for a German.
Hey Rob, I think when you start your share screen, there should be a little menu thing that pops up, and one of the boxes is to like play audio through the internet for like your YouTube video and stuff. Yeah, I'm not exactly sure how to do it, but I'm pretty sure when you open your share screen, there should be a little menu, but it's okay. Yeah.
All right, I'm looking.
Yeah. I think it's like when you click it to share your screen, then it'll pop up. I don't know if someone else knows.
Optimize screen for sharing video clip. There it is.
There you go.
I'll mess around with that later.
Yeah.
All right, everybody have a chance to watch that? Well, the point of that video was at the very end of that little clip, he's talking about the Battle of Britain. He's talking about the air defense system that was revolutionary at the time. They were the first country to develop such an air defense system, set up through radars, observers, and communications to a central location where they then told their Air Force pilots where to go. And it was fairly complex at the time. And what he's discussing is he said, well, if you guys basically work this system correctly, the system's been proven, it works, and if you're no good, the reason is because it isn't the system, it's because you're no good. So if things don't work, it's because you're no good. And that's kind of what I'm trying to get across with the steps is if you use those steps, you'll do well. What I have seen that people who skip the steps because they think they know the answer already tend to make mistakes. So just trying to emphasize the point that you're going to use those steps today and that there's a reason why we use those steps and there's a reason why checklists and formalized methods exist. It's not because we're trying to stint your creativity. It's that we're trying to make sure that you get to the right solution. Today we're going to be doing basically 4 little different problems. We're going to be looking at reactions at a pencil, some guy, me, sitting in a chair, some guy sitting on a bicycle, and a bicycle. So we're going to work through those problems. But first I'm going to do an example problem. If you go to your next page, this is the simple problem that I've got drawn up on the board. Let me go to that real quick. Actually, we'll just use this. So this is a pretty simple problem. Like I said, this is the kind of problem you should be able to really do in your sleep at this point pretty soon. And hopefully by the end of this lab, you'll be able to do this. So as I said, we basically have 3 sort of basic tools at our disposal. We have our knowledge of connections, we have our knowledge of free body diagrams, and we have the knowledge of the equilibrium equations. And by using all 3 of those things through these steps, we should be able to solve this problem quite easily. So I'm going to do this problem, and this problem, what it says is the beam is 2 meters long, so we have L, which is 2 meters. We have a force of 120 newtons, and we know the reaction on the on the right-hand side of 85 newtons. And we don't know what distant A is, and we don't know what the reaction at the pin is. So if we use these steps, the first thing it does is says, well, what are you given? Well, we're given the sketch geometry. We have that all up there. And then we've been given some information that's written right here, and we repeat all of that. And then what are we looking for? In this case, we're looking for distance A. We want to know how far over is the force on the beam to cause a reaction of 85 newtons on the right-hand side with a force of 120 newtons. Pretty straightforward. So we're looking for A. What you do is you first do, the third step here is to label the diagram. Just write on the diagram, just draw away. This is not, I repeat, this is not your free body diagram. This is you labeling the diagram so you know what you're looking at. Because there's pieces of information that are missing up here, and you're going to basically write on them. So I have assigned the two sides, nomenclature A and B. So now on the right, I have my known force RB of 85 newtons going up, and it's a roller. So it's only going to have a vertical force in it, normal to the ball, basically. And then on the left side, we have a pin. So we can have a reaction RA and an RAY and a reaction RAX. We know what the length is, 2 meters, and I should have put in here, my diagram's missing it, F equals 120 meters. I probably should have put that in there. So, and we don't know A, we leave that blank. The next thing to do is to create this table of forces and what you know and directions. So if I look at F, it is given in the problem, F is 120 newtons. We know the direction is straight down. RAY, I should say, reaction at A in the Y direction. We don't know. In fact, that's something we'll need to solve, but we don't know. That's not what we're asked for, but that's what we need to solve at some point. And then we do know its direction because we've assigned it as straight up and down. If we look at the reaction in the X direction at A, RAX, I'm just going to say it's 0 because there are no other forces in the horizontal. So we can just say it's 0. We do know what it is. It's 0, and it's in the X direction. So we'll be able to ignore that in the future. We know the reaction at B because we're given that. RBY is 85 newtons Y. And then lastly, we don't know A. We don't know its magnitude. We do know its direction. It's along the X direction. So,
I have a question.
Yeah.
That on your table, you have a distance. You have a distance A. And I don't think we've ever included that before. Is that common to have other attributes like distances on your table like that?
No, and it's why I included it in this problem. Normally, you would be solving for the reactions and you would be given A, but I wanted to do it this way because some of what you're doing today is going to be doing that. It would be, in essence, not knowing the direction of a force. So,
okay.
But yes, I put it in there because it's an unknown that you're solving for. So, usually the geometry is given. That's usually the part that you do know, but in this case, you don't. So if we go to number 5, this is sort of the important aspect of knowing whether this problem can be solved or not. The number of unknowns is 2 and the number of equations is 2. And so some people say, well, why a number of equations of 2? In a 2D problem, we usually have 3 equations available to us, and why am I only listing 2? Well, the other equation would be the sum of the forces in the X, and we've already determined that it's 0, so it really isn't available to us. That equation will lend nothing to the problem. So we really only have 2 equations available to us. And we need 1 free body diagram. And really, that's the only thing we've got available to us is 1 free body diagram, unless we start drawing just the roller or just the pin. So we're going to select our free body diagram. In a case, like I said, we only have 1 really available to us, and that's the beam. And this is what the free body diagram would look like. So, and again, I should have said F equals 120 up there. But we don't know RAY, and we don't know A. So in our free body diagram, those are the 2 unknowns right there. And then this is all the rest is the geometry and what we do know. Here in number 8, it's talking about basically checking the components of your forces. to make sure that they equal 1, both 8 and 9. Because we only have directions in the y, there is no need to check our components because we really don't have any components. We just have forces in one direction. So 8, 9, you kind of get to skip in this part. So what equations do we have at our disposal? Again, like I said, we only have 2 really. The sum of the forces in the y, and the sum of the moments, and we can choose them wherever we want. And in this case, I chose A, and I'll discuss that in a little bit. But the sum of the forces about y is pretty straightforward. We have RAY, we have RBY, it should be this one here, and F. And notice how I said equals to 0. I didn't put F on the opposite side. I started off with equals to 0, and then I put all the forces on the other side. Because the sum of the forces should always equal 0. And I strongly, strongly suggest that you always use 0 on one side and then put all your forces that you're summing together on the other side. A lot of times what people do is they put the force over there and they somehow get a negative or a positive confused. And then when they solve it, they end up with the reverse, basically reverse polarity of their force. And then when they go to solve the rest of the problem, all of their answers are wrong. So I strongly, strongly suggest that you always say equal to 0 and then sum all your forces and then move the forces around as you required in this equation right here. It's really quite easy to see that RAY is going to be equal to 35 newtons, which I've got boxed down in the solution down there. But it's really not what we're looking for. We're really looking for A. And so we have a choice of where we're going to take our moments, because we can take our moment anywhere. We could take it in the middle of the beam. I don't think that would be very fruitful. The most logical places to take a moment are where forces are acting. And so in this case, it would either be here at A or at B or even at F. Now, doing it at F probably isn't going to be very helpful. Just because you have to somehow balance RAY and RB to make things work out. I think, yeah, right. So what I did was I chose RA, what did I choose? I chose A. I chose it at A. So I don't even have to use RA. So in this case, I wouldn't even have to solve for RAY, which I did here anyways. I could just use this equation right here. And if you look here, I've got the reaction RBY times L, which is this force times this moment arm. And if I use the right-hand rule, you'll see that that's a positive moment, which is why it's labeled positive. And then if you look at F, it's F times this lever arm A, and it's going to be a negative moment from the right-hand rule. And those two things sum together need to equal 0. From that equation, I can solve for A directly, and it should be 1.42 meters. Now, like I said, you didn't even need to solve this upper one here. You could have saved yourself some time and not solved that at all because we weren't looking for the reaction in RAY, just A. So if you have any questions, now's a good time. Hopefully this is not new. This is review, which is why I kind of shot through it really quickly. So this is, again, the same problem. If you have any questions, now's good. Otherwise, we'll move on. Attributes are unknowns that come up. Yeah, there you go. All right, I'm going to go back to sharing my screen. We'll go over the actual assignment. So I'll go through each of the parts that I'm looking for you to solve, and then we'll go from there. We'll do breakout groups. So first of all, the pencil leaning against the wall. Here's your pencil. leaning against, whoops, I got to share. You guys see this one? Yeah, all right. I got my other camera in the background there, not me.
You good?
Let me just change that real quick so you see me yammering on. So here's your pencil leaning against the wall. You'll be given the length of this. You'll be given the weight and the location of the center of gravity and the angle. And what I'm asking you to do is solve for the reaction at this wall. And we'll consider this to be a frictionless contact point. And down here, we'll consider this to be a friction point. It would look, the connection would look like a pin. And this would look like a roller. We're going to solve for those reactions. You can follow through on the problem, but basically there's the weight, there's the distance of the pencil, here's the angle, and from that you should be able to solve that first problem.
Rob?
Yep.
Just to confirm, you said that the pin was at the bottom, at the base of the pencil?
Yes,
and
right
the
here.
roller was on the wall?
Roller up here, a pin down here.
Okay, awesome.
Those are what the connections ought to look like. It's a friction, so it'll have both a vertical and a horizontal, whereas this should just have a horizontal.
Awesome.
Assume this
Thank
is
you.
90 degrees, the wall. Didn't say it anywhere, but anybody that's thinking differently. So here I am sitting on a chair. What I'm going to try and get you to do is to find out where my weight is reacting on these two relative, I should say, where is the weight in the horizontal, and that's side to side. Where is that weight relative to the front leg? Where is that W acting, and how will we do that? First of all, I'll give you my weight, which is scary. I'll give you the weight of what the chair is on the front leg. So this is sort of the reverse situation. Instead of the right leg, you now have the left leg of the problem we just solved. It really is identical problem in the sense that now you've got my weight and you have the reaction on the left side. So rather than some force, it's now my weight. We're going to assume that the chair is weightless for the moment. All right, and so there's the number on the front, that's the force reaction. We're also going to assume that these surfaces here are frictionless, which is far from true, but we're going to make that assumption anyway, partly because there really would be no horizontal force going on here. It's all the forces are in the vertical. So we can make that assumption even though it's not really a frictionless surface. Assume that it is. So that's like being on rollers again. What was the other assumption? Oh, the other assumption that I want you to make, and again, this is all written in there, is that normally on a chair, you've got a right and a left side, and we're only looking at the left side. So we're going to say that all of the forces are in half. So all the right-hand side versus the left-hand side are mirrored, and half of the forces are on the left, and half of the forces are on the right. So in essence, use half of my weight to solve this 2D problem here. So take my weight and divide it by half when you're looking at reactions. And I go through and I take some measurements. Normally I would have you guys in class do these measurements, but here are the answers. So really that's the only geometry you need is the distance between the two, and you should be able to solve the rest. The next is a bicycle. We're going to solve for the reactions at the wheels and where the center of gravity is for both the bicycle and for myself. We're going to assume that the problem is two-dimensional, which again is not, this is not a bad assumption here. It should be just fine. Again, we're going to assume that the ground is frictionless. So there are no horizontal components acting on the wheels. Otherwise, we'd start rolling along. Anyways, I'm not sure if any of you are familiar with this. The next thing I want to show you is how to get the center of gravity, really of anything, but in this case, a bicycle, through what's called an empirical method. It's not through any calculation of a whole bunch of center of gravity's weight to discover where the center of gravity is based on all those locations. It's just taking the entire object, and what you do is you basically hang it from a rope, and you just continue drawing lines straight down from where the rope is through the body, and eventually, if you hang in enough different locations, the intersecting points will describe the center of gravity, and I've got this sort of laid out here. So what I did was I hung my bicycle, just like I said in this first photo. In the second photo, what I did is I put some paper on my bicycle so I could draw a line from the extended line that the rope is making straight down. In fact, I've got you can see a plumb bob, a chalk line plumb bob going down through this paper. And so I'll draw a line on that paper. You can see here's the first line. And then I hung it from the seat post rather than the stem. And again, here's my plumb bob. And it goes down, and I've got an intersection right there. So in theory, that should be my center of gravity. I like to do it a third time to make sure that I didn't goof up, because if I do it again a third time, it should also intersect. And this time I hung it from the bottom bracket, and you can see that again, it did go right through here. So here I've got my center of gravity. So there's the plumb bob and the third line. That's my center of gravity. So that will give me the location of the center of gravity for the bicycle. And my question to you as students and your knowledge of connections and the sum of the forces and so forth is, why does this method work? And it's all about the connections and your sum of the forces. Why does hanging it by a rope work versus, and the key question would be, versus say a clamp? So why does that work? Then I go and I measure that center of gravity, so you know where that center of gravity is. So at this point, I'm asking you, given the weight of the bicycle, to tell me what the weight on each tire would be, the force, the reaction at each wheel. Given that you know where the center of gravity is, and the length, and the weight of the bicycle. So this again is very much like the problem that was in the example, almost identical. So there's this problem that I was just describing. Lastly was, I shouldn't say lastly, next to last, is to determine the horizontal center of gravity of the rider. So when I get on this bicycle and I know what the reaction is at the left wheel, I know the weight of the bicycle, I know the weight of the cyclist, I should be able to determine where my center of gravity again. This is again, just like the problem that we did in the example, except for now, instead of having one force, we have two forces. One of those forces, we know exactly where it's acting. Only one of those forces, we don't know where it's acting. We need to get that horizontal distance. Again, I'm not concerned about vertical location of center of gravity, only the horizontal. And then lastly, this is exactly the same problem again. Where is the equivalent force for both the bike and the rider based on this information? And this should be, like I said, exactly like the problem that we did in the previous example. So this is sort of the same problem 3 times over, with one small addition on the fourth one with the pencil, which is a little different. I want you to use those steps in each one of these, with the exception of part 3D, because you will have already laid out everything for part 3 quite well.
Rob, on the last one, we don't need to do the dividing in half idea, because the dividing in half idea was because there's 2 sides of the chair,
Yes,
but
correct.
the bike is all on those 2 points, right?
Yes.
Okay, just checking. Thanks.
One other thing about that chair is I know you guys are submitting it to me and you should have a digital copy, but keep a copy because next week we're going to look at the internal forces on that chair. We're going to start looking at the forces of that chair. So you'll need to save your solutions for that problem for the upcoming lab. Otherwise, you'll have to redo it. Not that it's a huge deal to redo those problems, but it'll save you some angst if you already know the answer. So, the reactions. So if there aren't any questions, I'll put you guys into breakout rooms.
Can we
Robert?
request people to go in a breakout room with?
What's that?
Can we request who we go in a breakout room with, or is it random?
I can assign manually, but with 35 people, it's kind of a pain in the butt. I can kind of move
Fair
around.
enough.
Yeah, I
Fair
understand.
enough, no worries.
Hey, Rob.
Yeah.
On the first one, when you said that the eraser is like a pin, so it has a vertical and a horizontal reaction, you also said there's friction, but are we assuming that the friction is like represented in the reaction, or should we include the friction as well along the reaction?
Yeah, well, hang on a second. So if we look at just the pencil end, if we just said it was friction, and this is really the right way to draw it, I was saying it, and then we would have a normal. If you drew a pin, you would have, excuse me, so you end up with the same thing. You know, instead of RY, you end up with N, and instead of RX, you end up with FS. I prefer to see it this way because that's more relevant, but the end result is you end up with two reactions.
Okay, cool.
Yeah, whoever asked about moving into groups, I can kind of move you around once I've set you up. I can say if there's like, if you have like one person you really want to be with, I can move you to be with that person. It does get a little bit complicated if it's groups of 3 or 4 that are trying to get together. So, I'm going to set you out. Are you there, Daniel?
Yeah.
Okay.
Hold on. Let's see. So I'm kind of like not really that good at doing the setup. Like I started the homework this week and I still have problems with it. So I'm not really that comfortable with this type of subject. So I just have a few questions for the pencil. Basically I have a normal force here and a normal force over here as well. Are we going to be including those in the diagram?
Mm-hmm.
Okay.
But you have one force there on that right-hand side.
Can you repeat that?
Bottom of the pencil there.
What?
Hey, look at your drawing there.
Yeah.
Kind of a mix of a diagram and looks more like a free body. But anyway, if you just look at what's counteracting NA, you don't have any other horizontal forces. So what's going to have to happen at B?
We're going to have a vertical force.
We're gonna have a horizontal force. If you did the sum of the horizontal equation there, you'd end up with NA equals 0, and we know that's not true.
Okay.
So you have to have something horizontal at point B, and in this case, it's friction.
So this would be a reaction force.
Yes, you'll have two forces at that B point. Okay, I would actually draw, this is what I would do, is I would draw it as a friction force going to the left because you're resisting the movement. And do it as a FS is friction static. There you go. Usually you draw it at the point, but that's sufficient.
We wouldn't be having friction on the wall, right?
No, we call that frictionless. If you read the problem, that.
Oh, okay. Okay.
Once we draw that friction point up there, to be honest with you, it becomes indeterminate. Can't solve
Okay.
it.
All right. Thank you.
Yeah.
Hey, Rob.
How do I?
Nope. Sorry.
Go ahead.
Breakout room 2 only has a couple people. I saw some of them have 4. Maybe throw one person into 2, just because.
I'll take it.
I think you're already in breakout room 5.
Okay.
I think if you could just join yours.
And why is that? I don't understand how it
Yeah.
divvies people up.
Yeah, there's 2 groups with 4 and 2 groups with 2, or 3 groups with 4. That's weird.
Alrighty. Well, let me go ask. I don't want to force people into.
Yeah, I mean, it's not that big of a deal. They seem like they could use another person.
All right. Would you want to handle rooms 1 through, I don't know, 1 through 4, 3, somewhere in there? We can always be in the middle. But if you go work
Yeah.
one forward, and I'll work 8
Cool.
down, 7 down.
All right, I'm gonna jump in one.
What did I miss that? Gonna go get some coffee.
It is on.
I said it was.
Oh, you said
So, but nobody's watching. Somebody asked. Now I get to.
This meeting is
Hey Rob,
Hey, I.
could I possibly go into whatever breakout room Tim's in? Tim Lotz.
Yeah. Yeah. Yeah, it's kind of weird. I do another thing. I won't discuss what it is, but for breakout rooms, and I specifically put people in particular places, and it's quite a task actually.
Yeah,
But moving one person's a piece of cake. And where are you? Oh, I see. And you wanted to be in with Tim?
Mhm.
Yeah, you're going to the right group for sure.
Oh yeah.
They are all the people who are doing well are in this group. I don't know
Oh,
how
nice.
that works out, but
Yeah.
smart folks. Don't get to room. There you go.
Sorry, I thought you'd already signed.
Yeah, I don't know what happened there, but it looks like you can go now.
There we go. Yeah.
This meeting is recorded. This meeting is recorded.
Really elements. Wow. Wow.
Does that mean we're all done, Rob?
Yeah, Yeah, if you guys need additional help, Andrew's in the STEM Center
Cool.
Zoom room. So,
Okay. Take it easy, Rob. Yeah, thanks.
yeah, thanks, guys. Hope you guys have a great day.
Bye.
You
Thanks,
too.
Rob.
Too.
Thanks, Rob.
Thank you, Rob.
Rob, is it possible to let us keep the room?
I can let this just drag on, sure. I'll stop recording though.
Yeah.